Today we're going to work with logarithmic functions and the characteristics of their graphs. And to get that started, I'm going to remind you of what we did earlier in the unit. So this right here are the exponential characteristics we talked about earlier in the unit in 2.3. We talked about an exponential function looking like this when it's an exponential growth and this way when it's an exponential decay. In both of these cases, we had a horizontal asymptote right here on the x-axis. Now, we're going to switch over to our logarithmic, and in the last couple of lessons, we've learned that logarithmic functions and exponential functions are inverses of each other. So the characteristics of their graphs will have inverse relationships. So from our exponential, who had a horizontal asymptote, our logarithmic has a vertical asymptote. Remember, they are a reflection across that y equals x line. So if my y equals x line is right here, my exponential looked like this. And so there is that reflection. Now I'm going to go ahead and erase this just to have a clean sheet here of our logs. This is the general form of the logarithmic equation, a times log base b of x. And so if we had a parent function, for example, of 2 to the x when we were talking about our exponentials, that's going to be the same case here. This number right here is going to be our parent function. So log base 2 of x would be the inverse of that 2 to the x. Since we have a vertical asymptote on the y-axis, then our domain here is from 0 to infinity. It does not touch the vertical asymptote, so that's a parentheses. We don't want to include that point. And then our range would be from negative infinity to infinity, so all real numbers. This was when the a value was greater than 0. So this right here was positive. If that value is less than 0, we have a negative there. Remember, that's a reflection across the x-axis, so it would look like this. I will have a vertical asymptote still on the y-axis. All right, for these graphs, it says logarithmic functions are always increasing or always decreasing. Again, we don't have that switch from increasing to decreasing, so there's no relative or local extrema. Unless there's a closed interval, then we include those values at the end. But for example, this one is always increasing. This one is always decreasing because as my x gets bigger, my y is getting bigger here. And as my x gets bigger, my y gets smaller here. So always increasing, always decreasing. For concave up and concave down, logarithmic functions are always concave up or always concave down, just like the increasing and decreasing. So there's no point of inflection because it doesn't change in that concavity. This right here would be my concave down. This would be my concave up. All right, for the end behavior, logarithmic functions in general form as the input values x increase without bound, the output values y increase or decrease without bound. So as my x's are getting bigger here, my y's are getting bigger. As my x's are getting bigger, my y's are getting smaller. So they are moving towards either positive infinity or negative infinity. Now, since logarithmic functions have a restricted domain, and we've got that vertical asymptote at x equals 0, then the left end behavior will occur when x is approaching 0 from the positive side or the right. So we will be going back to some of that other limit notation that we've used. Here's an example of one of the limit statements. It tells us the limit as x approaches 0 from the right-hand side, that's what that positive means, of my function is either going to go to positive or negative infinity. In this case, it's going to negative infinity because it's going down on this side. In this case, it is moving towards positive infinity. And so this number will change when we do transformations to wherever the vertical asymptote is. Then for my right side, it's either going to be moving to it's going to be moving to positive infinity here. And again, it will go either to positive infinity or negative infinity. Here it's going towards positive infinity. Here it's going towards negative infinity. And so that's one of the things we really want to focus on writing today because you do want to have those limit statements written correctly. And so we'll practice with graphs and equations. On this one here, graph of f of x, it wants us to write the two limit statements. So on the left here, we've gone ahead and written the first one for you. It says the limit as x approaches 0 from the positive side, so from the right side, f of x is equal to what? So that means as we're approaching this way, This is from the positive side to my 0. Well, my graph is going downward. So my answer here would be negative infinity. Now we're going to move to the right-hand side, and that one we didn't have a statement written, so we're going to practice writing that ourselves. So on the right-hand side, we want the limit as x approaches infinity, because it's going to the right, my x values are getting bigger, of f of x, that's my function right here, and the limit as my x gets bigger, my y is getting bigger. So this is moving towards positive infinity, so we would say positive infinity there. All right, now we're going to write them from the beginning. So on this one, I would say the limit as x approaches 0 from the right-hand side, so I need a positive there, of h of x is equal to, well, this graph is going upward. So this is a positive infinity. And then on the right-hand side, I would say as x approaches positive infinity, because it's moving to the right over here, of h of x. Now this graph is moving down, it's decreasing, and so it is moving towards negative infinity. Now, the third way here is from an equation that we want to write the end behavior from. And so you can go ahead and write it straight from that, but I suggest you sketch a graph. It's much easier if you think about what the graph would look like. It doesn't have to be a great sketch, but just give yourself a sketch. So it's got log base 3 of x is our parent function right there. It's got a vertical stretch by 2. That doesn't really change the end behavior. Since it is positive, it's going to stay like the parent function on that one. It does not change the vertical asymptote either. So we've got a vertical asymptote right here at 0. And then it's got a vertical stretch, so it's going to go up a little bit faster than the regular one, but my graph looks like this. Now I can write my limit statements. I say the limit as x approaches 0 from the right-hand side of g of x, it is equal to negative infinity, because this is going down. Then we've got the limit as x approaches infinity, that's the right-hand side, so which way is it going to the right, of g of x is equal to positive infinity, because it's going upward here. So end behavior is a really important part of this, and the notation is crucial, so we wanted to practice that and make sure that you can see where that's going. All right, so on this next part here, we're going to talk about the concavity and increasing or decreasing. So when we look at this graph here, it says concave up or concave down. This right here has a concave up. It is facing this top part here. This would be an example of concave down. And then for my last one here, again, it doesn't say to sketch a graph, it's just asking you to answer the questions, but I suggest you sketch a graph to see what that would look like. And so here we have not moved to the left or right, and so our vertical asymptote is still at 0. It does have a reflection across the x-axis here, and so my graph is going to go this way. And so there is my graph. This right here is an example of a concave up. Now, for the increasing or decreasing, as my x values get bigger here, my y values get smaller. So this is decreasing. On this one here, as my x values get bigger, my y values are getting bigger. So this is increasing. And then for my last one here, as my x values get bigger, my y values get smaller. So this would be decreasing. Now, I know it doesn't say it there, but just a quick reminder of what we learned in that first unit. So this right here is concave up. So when we're talking about the rate of change, when it's concave up, its rate of change would be increasing. So this is decreasing at an increasing rate. This right here would be increasing at a decreasing rate because it's concave down. So I want to keep making sure you go over that vocab over and over again. All right, for example 3, it's the selected values of the several logarithmic functions are shown in the tables below. For each table, find the value of the constant k. So on our tables here, and we worked a little bit with the exponential tables, so we're working with the logarithmic now. When I look at the patterns here, these are going up by equal lengths right here. But my x values, that multiplied times 2, And then if it multiplied times 2 again and times 2 and times 2, I can find a pattern there that the x values are being multiplied by 2. So this would be, my k value would be equal to 4. That would make it a logarithmic function. So let's talk about that. With exponentials, my x's had an equal length interval and my y values had a common multiplier. With logarithmic equations, your x values are going to have a common multiplier and your y values are going to go up on an equal length intervals. So when we look at our second one here, think through what's happening on these. From 6 to 18, we multiply times 3. From 18 to 54, we multiply times 3. From 54 to 162, again, we multiply times 3. And so if I wanted to go back and figure out what was k, if I'm multiplying times 3 this way, I would divide by 3 here. So my k value is equal to 2. Just for reference, that number that's being multiplied, that would be our base on the log. And so if I wanted to write this equation here for practice, I would say this is a log base 2 of x, and then it has shifted up 1 unit. Remember, the first value on our graph should be 0, 1, and so this went up to 1, 1, and so we know there's a vertical translation there of 1. We'll go back to writing equations a little bit later, but that's just where that value is coming from. And so the parent function for this one would be a log base 3 of x, since we were multiplying by 3. All right, this one is not quite as easy to see the multiplier. And remember, we talked about those on exponential ones as well. When you can't find the multiplier that fast, you can find your differences and then check. So this was 1, 2, and then we don't have anything here and here to figure that out. But if we think through this multiplied times 2, and so then the next one would probably be 4, and the next one would probably be 8. We're multiplying times 2 each time to get it here. And so let's look to see if that works. So we multiplied times 4 here, where the difference would be 4 to get a common multiplier of 2. That would make this 11, and then that would make that 8. And so we have a common multiplier of 2 right here. So our parent function would be log base 2 of x. This one's a little bit more complicated to write the equation, but all we needed was the k value, which is 11. All right, and this one looks tricky here. Again, we have the equal length intervals on the x value. We've got the e's are the ones on the y values. I'm sorry, the x values. Now we do see an e here, so I know already that my k value is going to have a base of e. The multiplier is not coming from that part right there. It is coming from what is happening up here to get to these values. And so we can see that from 7 to 10, that was a difference of 3. Right here from -2 to 1, because when nothing's written there, that's a 1. There's also a difference of 3. And so we know that this would have to have a difference of 3. So that would be e to the 4th power. So getting that common multiplier and really understanding that the common multiplier for logs happens on the x's. For exponentials, it's on the y's. For logs, it's on the x's. So make sure you understand that part of it. All right, for the domain and range, the final part that we're going to talk about on these characteristics of logarithms, you do have to think through our or sketch the graph of what that's going to look like. So this right here, no movement to the left or right, so it is still going to have a vertical asymptote at 0. So our graph would look like this. So our domain is from 0 to infinity, and our range would be from -infinity to infinity. All right, just to practice that end behavior one more time, we would say the limit as x approaches 0 from the positive side of f of x. We said that's going to be at the bottom here. So that would be -infinity. And then the limit as x approaches infinity of f of x, it would be positive infinity. All right, for the sketch on this one, this did move to the right. We've got a horizontal translation of 3. So my vertical asymptote also moves right or left with that. And so it is now at x equals +3. my vertical asymptote is. We've got a reflection across the x-axis here, and then we've got the vertical stretch. So this is going to look something like this here. So our domain would be from 3 to infinity, and our range would be from negative infinity to infinity. That's going to be true for all logs, because remember, they are the inverse of exponentials, and so our domain for exponentials was all real numbers, and so our range for logs is going to be all real numbers. So I can already tell you this one's negative infinity to infinity. All right. For our left end behavior, I would say the limit as x approaches 3 from the right-hand side. So this is where that number changes. Because my vertical asymptote is here and nothing has moved to that other side, this is the part we're approaching. And it is up there. So it is going to positive infinity. And then the limit as x approaches infinity of g of x, in this case, would be going to negative infinity since it's down there. So really going ahead and graphing that really helps out. All right, and this one is pretty tricky because they gave this to you without factoring it. So the first thing you would want to do is factor that. I've got to factor out a 2. And so when I do that, that's going to be an x there. And then that is going to be a 3/2. So I factored out the 2 so that it did the correct general form of the transformations. So we've got a vertical dilation by 8. We have a horizontal dilation by 1/2. And then we have a horizontal translation by -3/2. All right, so -3/2 is right here. So that's where my vertical asymptote is. And then we've got our horizontal and our vertical translations, but our graph is basically still going to look like this. And so my domain would be from -3/2 to infinity. My left end behavior would be as x approaches -3/2 from the positive side of h of x. In this case, that is down there at negative infinity, so that's going to be my limit there. And then my limit as x approaches positive infinity of h of x is equal to positive infinity. So that goes over some of the characteristics. You should be able to identify the domain, the range, the end behaviors, so our left and right end behaviors. You should understand that these logs have an input value that has a common multiplier. And so that base right there is that common multiplier in your inputs. You should be able to identify the concavity and whether it's increasing or decreasing for logarithmic graphs. And at this point, exponentials as well, since we already did that.